Well, hello there again, friends. Today is 9/28/2022, and today is the Odin Project Vlog Day 150. And I am on part 2 of Project Night Travails. And essentially, not essentially, I did get through 2, 3, and 4, highlighting and lumping them all together. We're basically choosing a search algorithm and finding the shortest path between starting square node and the ending square node. And output whatever the path looks like. Technically, at this point, I am done. I have successfully got this output to come out like that. And we'll go over that in the code here in a moment. But just letting you know that I may or may not, we'll see. Because technically I am done because I got this to work. But I chose my algorithm and it works fine. But I might finish up with the visual part because right now it's like it shows here. It's kind of command line console logish. It's not doing anything in the DOM. There's nothing to click. There's no quick events. Reason why I say I may or may not do that because I really don't want to get bogged down in extras on this, and I really like to move on into intermediate Git into the next section. But I might give it a shot and see how long I spend on it, and if it's not too bad, I might make another video as a part 4, or excuse me, as a part 3, and call it good. Otherwise, if it gets to be too much, if it bogs me down too much, I'll just scrap that, and we'll move on to intermediate Git together. So that's coming up for the next video, just to give you a heads up. So anyway, let's hit the editor. Alright, so I'll blow this up a little bit so you can see it. Alright, so I decided to employ the graph breadth first search algo for the moves. And so that's what that's the algo I chose for that best fits the knight's moves. The two up, two up, one over situation. So I start off by making a constant variable square at registry equals new map. And so what the map does is it holds key value pairs and remembers the original insertion order of the keys. So I'm using that. I got that off Google searching. We've not been exposed to map yet, but so basically I'm using that, and that's invoking from square registry. And so square registry is going to be a map that holds key value pairs in an array, basically. And I'm going to use that as what it sounds like, as kind of like my holding point for my squares, and remove them as necessary. And then I'm just going to go down the code base here from top to bottom. Although the flow control doesn't really work like that in this instance, but some of it does. But it'll make more sense at the end because I put my my main function, my Night Travails, at the bottom. So and then some of that stuff's called back from up here. So I did that on purpose because, as you know, if you try to call a function or anything really before it's defined, you'll get an error. So anyway, we'll go down here. First part here, we're going to get set current chords to the board. So there's a function called chess square, and it's going to take in x and y coordinates, and just simply creating a constant x position and y position equaling those coordinates so that we can get them off x, y. Using that because this is a dynamic function that's going to be taking multiple x, y coordinates, and so I need them to change on the fly. And then I have a let predecessor with no, just creating that initial variable with no instantiating it, basically with no value. Define the array for hard-coded possible moves of the knight. So this is creating a constant array of basically possible knight moves. So basically, these are all the variabilities of the way the knight moves, both 1, 2, 2, 1, and then the negative predecessors of that. And so we'll use that, or I'll use that in the code here to help make the move, as you'll see here momentarily. I have a constant get predecessor, and that just simply gets the predecessor as it's set down here farther in code. So I'm only calling get predecessor when it's appropriate. When there would be a predecessor to get, and you'll see that as appropriate in the code. And I have set predecessor, which takes in a parameter of new predecessor. And so when this is called, the new predecessor comes in and evaluates. So if new predecessor is present and it has a value in it, this is what calls here. So predecessor will equal predecessor or new predecessor. So basically, if there's a new predecessor and this intake parameter has a value attached to it, predecessor will become the new predecessor, if that makes sense. Otherwise, if new predecessor is not available, there's nothing in the parameter, the variable doesn't exist, whatever, then predecessor will be set to the itself, to the current predecessor. So that's that piece of logic there. Is some of this, again, just stay with me, some of this will make more sense as we get down to Knight's Travails, but to that particular function block. But so we have a constant name, and this is just a temperate literal that shows the XY coordinates, and just calling it name, and that'll be used throughout. Next section is evaluates the current possible knight moves against offsets. So I have a constant possible knight moves, and it returns knight moves, and then before it returns the knight moves, which is the the constant array of possible knight moves up here, it does a map. If you remember, a map calls a defined callback function on each element in an array and returns an array containing that result. So we're going to run it off offset, and then the callback function it's going to call is new square form, which is, we'll jump down real quick, which is right here. And this calculates a new set of square coordinates against the offsets. So it takes in x offset and y offset that is below, and actually it will be below, but the offset here is at position index 0 and index 1. That comes from below in the other function, and it's basically going to add the x and the x position x offset and the y position the y offset together. And so then there's this funky looking if statement. So basically, if the new x is greater than or equal to 0, and new x is greater than 8, and 0 is equal to or less than new y, and y is less than 8. So basically, what that's saying is if the offset, if the mathematical offset is basically between 0 and 8, it is a valid move. This if challenge keeps us from bleeding off of the chessboard and having basically a runaway infinite loop of code. So this keeps it from doing that. We're going to return chessboard new xy. So if that's true, it returns true. We're going to return chessboard or chess square, excuse me, which comes back up here and calls chess square with the new coordinates, and we kind of go through that process over again. And that's new square form. So coming back up here, so we're going to invoke that new square form using the offsets, and then we're also then going to filter. And filter, if you remember, returns the elements of an array that meets the condition specified in the callback function. So this is going to returns the elements array that meet the conditions. So we're going to basically say we're going to create a new parameter called square, and if square is not equal undefined, we're going to filter that out. So basically, if there's any square parameter filters in here, any filtering, if there's any squares that end up being undefined, which, as I just explained, would mean that they're greater than 0, less than 0, or greater than 8. So it does not satisfy this if statement. They will be undefined, and so we want to filter those out. And then we return that knight moves filtered, mapped and filtered array back out. Kind of half doesn't make sense, I know, because again, this is being called and used from the Knight Travails down here, so it'll make more sense in a second. I'm just kind of going through this top to bottom so I don't miss anything. So then we have get and set map constructor object names. So here we have, this is what I was talking about earlier with the map function. So we have an if statement. If square registry has names, we're going to call that name that we had up here, a constant name here. So basically it's going to retrieve the xy. If the xy has, and has is not something we've used, or I've used, and we've not used on this channel. Has is a map key that basically is a boolean that indicates whether an element with a specified key exists or not, and that works in conjunction with that map function. So basically we're asking if the square registry has the name of xy, we're going to return the square registry, and then get is the method that returns a specified element from the map. So we're going to basically go get. It's kind of similar-ish to await and fetch and promises. So ish kind of, you know, it just I'm sorry, not that. Scratch that. It's kind of like when long time ago when we worked on local storage and web storage. So we're kind of getting and setting. So this basically has is kind of your set, if you will, and then get is we're getting it. So we're retrieving that name, that XY coordinate, and into square registry and returning that. Else, if square registry does not have a name, we're going to create a name. Basically, we're going to give it property of name, get predecessor, set predecessor, and possible night moves, and we're going to set those objects to new square. And you see that there. So we have name, which is a string, get predecessor is any, set predecessor is any, and might have that new predecessor if its value is provided, and night possible night moves, which is another function that produces any array. So then we come down here. We have we're going to set the adds an element with a specified key and value to the map. So now we're going to set the square registry, and we're going to invoke the name. So we're going to get the XY coordinates, and we're going to also input new square into the set registry. So we're going to set the XY coordinate, which is the name, and then the new square, which is essentially a constructor, if you will, of key value pairs of name, get predecessor, set predecessor, and possible night moves, which also are self-invoking functions, or functions themselves. So we're gonna return new square, back out, and then down here is the meat and potatoes of how we really start. This is kind of the process, the flow control, as it really kind of comes in here. So we're going to intake the class coordinates or the click coordinates from user and run the search algo. So we have, it's called night travails is the function, and it's going to take in a start and a finish from the user. And first thing I'm going to do is clear out and use the clear method to clear out the square registry. So basically what that does is if there's anything that's in there in that map from before, it's going to wipe it all out. So we start fresh. So we start fresh each time we're called, because we're making a brand new move, and we don't want any old values in there distorting and polluting our search algo. And then we have two constant variables, origin and target, which call the square chest start and finish, and it's going to supply the start and finish that we supplied here as parameters from the user. And that's chest square is up here. So again, we're just creating those constant variables from xy and getting them out of xy and putting them into x position, y position, and creating that predecessor instantiation. And then we have constant q equals origin. So what this is going to do is take the origin from right here, which contains the chest square coordinates, and we're going to make, origin into an array by putting it into brackets, and that's going to become the q. So the q basically converts origin to a 2-coordinate array, and then we're going to do that same mentality. Skipping down here for just a brief jiffy. Same idea for path. Path equals target, so target will become path, and that will house the 2-coordinate array. So going back up here, we have a while loop. So if the queue includes the target, so basically if the target is included and inside the queue, and if you see bang here in front, which means not, so as confusing as that sounds. So basically, if target is included in queue but not included in queue, so we don't want to see it, we're going to continue in the while and iterate through, and we're going to create a constant variable current square equals queue.shift, and if you remember, shift removes the first element from array and returns it. So we're going to pull that. We're going to pull that right out. So whatever just got put into queue, we're going to pull that first one right out. If it's the first only set we have in there, we're going to take it out. And we're going to create a constant enqueue list, which is current square dot possible night moves is going to be what's in its value. So enqueue list is going to have current square dot possible night value moves, or possible night moves, excuse me. And so if you remember from earlier, that goes back up here, and we're going to do the map and filter off the night moves hard-coded array list, and that is going to be ran against current square that we got from the pulling from the queue, and that's going to be put in the variable enqueue list. So this is an incoming queue. And then enqueue list.forEach, so I'm going to loop through each one. So we're inside of a while loop. This is going to keep looping as long as we don't see a target in there. I'm going to keep looping through, and then there's a for each loop inside here that instantiates square as a parameter, and square.set predecessor, and we're going to give it current square. So what this does is sets the predecessor that we have up here. Just simply, as I said before, we have new predecessor. If new predecessor is not in a parameter involved, it's going to set predecessor to itself and continue on. Otherwise, new predecessor will become predecessor. Now, it's kind of a mouthful. Don't over-explain that. But so basically, in this instance, square, we're checking to see if set predecessor current square is going to become we're going to check the current square, which is enqueue list, and check to see if we need to set the predecessor, which one. And then after we do that, we have a queue.push anything. If you remember, triple dot is any argument, any number of arguments. So we have any number of arguments, and then enqueue list. We're going to push that enqueue list into queue, and queue is defined up here as the origin of that current loop. And so the same exact thing, the same methodology exists for the path for the target. The only difference is instead of shifting, we're going to unshift, which means we're going to insert instead of remove. We're going to insert new elements at the start array and return the new length. So basically, this is taking. We're getting the predecessor. We're setting the path of the position 0 to previous square. So basically, we're preserving it, and then we're adding it with unshift. Unshift is not something I've used before. I had to look that one up. It's very kind of weird to understand because unshift does not sound logical. It really sounds like something you would take out, not insert. So this actually inserts. So, and then we're console logging as per the requirements of the text. The shortest path was in just using a object literal here, path.length -1 to get the most recent or previous move anyway. So it's going to loop over that every single time and tell you how many moves it took, and then the moves were colon, and then we're going to do a for each over the path, and then each square is going to be console.log square.name. So we're going to get the coordinates of the name, and we're going to print them off on that for each. And that was it. So I went through that really fast. So please feel free to rewatch this for further understanding and cementing, because I did go pretty fast over all that. And then I export night Travails because I used it over here in app.js. So app.js here we have nice Travails, and I put in the example of 3.3 and 4.3 because those are what are in the example here in the sample. of 3.3 and 4.3. So, oops. So I have the 3.3 and 4.3 here. And so basically I'm mimicking user input because, like I said at the beginning of the video, I don't have that set up yet. So this is mimicking a user input, a click, if you will, on the board to move the knight. Again, like I said in the beginning of the video, I'm going to try to see if I can automate that on the screen. I don't want to get bogged down in it though, because since I've technically completed the project here by having this work and produce the shortest amount of moves and least distance, I've satisfied the requirement. But I just trying to sew things up and make things look good. Since I started off with visual, I kind of went in with a visual, but we'll see. I'm not afraid to move on either. Anyway, not to keep repeating myself. So 3.3 and 4.3 are going to be the start and the finish coordinates that we're going to input in the algo. And so that will come up here in the start and finish, and it will process through all this code. And so when you go out to the browser and refresh the page, you get the shortest path with 3 moves. The 3 moves were 3.3, 4.5, 6.4, and 4.3. Do you notice something different? 3.3, 4.5, 2.4, 4.3. So I actually done a little bit of digging because I thought maybe I had it wrong. This was a good example because I wanted to show you guys here on video that the search algo still is correct even if you don't get this exact order, because you did make it in 3 moves, and not only did I make it in 3 moves, but the 6.4 is still a valid input. So what happens is, so we start at 3.3. My mouse might be hard to see a little bit, but I'll wiggle it here. So here's 3.3. So we move to 4.5, which is 1, 2, and then 1. So we're up at 4.5. And then my solution was going to 6.4. So we go here, we go up 2, left 1, 6.4 is right here, and then we end at 4.3 as per the user's request. We go down 2 and to the left 1, and we end up at 4.3. So the solution in the example was 2.4. So for the sake of time, I'm not going to map that one out with my mouse. But basically, it's a valid. Obviously, that's a valid move as well. It's just going the opposite direction. You still get there in 3 moves. You just have a different position that you went to. Both are the equal length. One's not longer than the other. So just wanted to show you that. So in case you guys were working on your algo and you got something like that and it still did it in 3 moves, but you had one that was off and you're like, is that right? Yes. You want to check your algo first and check your logic to make sure that is correct, but that can be correct. So just wanted to iterate that. So this was a long one, and I'm glad I separated this video up. I actually was going to finish it with the visuals and everything, with the clicks here, but I'm glad I didn't, because that would have made this video incredibly long. I didn't think it would go 23 minutes, but I guess that's a new theme here lately. A lot to go over. So anyway, I will stop yapping. Thank you for coming along the journey with me today. Hope you learned something and stuck with me to the end, and I appreciate every one of you guys very much. And please like, share, and subscribe for more content, and let me know in the comments section how you guys are coming along with the algo and which one you chose to use. Did you use a map or like I did, or did you use a different method? And did you even use a BST, or did you use something else? So be interesting to hear from you in the comments on what algo you chose, because there's probably multiple ways to do this. One may not be better than the other. Just curious to hear from you. So anyway, with all that said, until next time, see ya.